Alright, so here we have a problem with a runner. There we want to measure information about how he's running. And we're told two things. We're told that the runner has a uniform acceleration for the first bit of the running time, and then a constant speed or zero acceleration for the second bit. We don't know how long he's accelerating for or what that acceleration is, but we know it's a constant for the first part, and then we know the second part is just whatever's left over. And our first job is to basically in parts A and B figure out an experiment that will do that will let us measure enough to determine those things, and then in part C show how we're going to use what we measured to calculate it. So really, you can't do any of these parts separately from each other. You need to think about all of them entirely. And when you write it, you'll probably have parts of B and C kind of intermixed. Really, you're kind of writing a lab report in some sense. Materials, procedure, and then the data analysis is the third part. So, there are also multiple ways to do this. I'm going to talk predominantly about one way with a couple variants in there. This is not the only solution, though. I'm not going to talk about every solution because it'll just take too long. So, when I see this problem, I think that it's clearly involving kinematics, right? We don't have anything about forces in here at all. It's just about describing motion. And we want to know stuff about time and acceleration. And we don't have anything like a motion sensor, right? When you look at my list of equipment, we have stopwatches that can measure time. We have tape measures, rulers, and meter sticks that can measure distances. Masking tape, string, and chalk that can be used for marking, and a starter's pistol that's presumably so everyone can sort of deal with time at the same time interval. And since it's kinematics, I know I'm going to measure something about time, so I'm going to have to use a stopwatch. There's no other way I can measure a time. So a stopwatch has to be in there. And then I have to use either a meter stick, tape measure, or ruler, because there's no other way to measure distance. And without a distance and a time, there's no way I can get an acceleration, because we know distance and time relate to velocity, velocity and time relate to acceleration. So in part A, I have to check off a stopwatch, and I have to check off one of the three distance measure things, no matter what. When I'm looking at this, I as we'll see, I'm going to pick the tape measure. I'll explain why, but it doesn't really matter. They're all pretty much interchangeable. So that's the first thing I think of, is what do I know about what those tools measure, time and distance? And I need to measure something from both of them. So we're told he's traveling a total of 100 meters. And so when I see this problem, I'm thinking we need to be able to measure acceleration somehow, which means we need multiple distance and time sort of measurements. There's no other way we can turn a distance measurement into an acceleration unless we have sort of multiple of them. And so if this is 0 meters and this is 100 meters on our course, what I would do is think of it as a motion diagram in some sense. How could we figure out where this guy is at in sort of as he runs? We know we have multiple stopwatches and 11 students, so I'd put students at various positions, right? I'd put a student here, and then I'll put some just tick marks. Let's see. 20, 30, 40, 50, 60, 70, 80, 90, yeah, roughly right. Those are meant to be evenly spaced. It's hard to do. So this is 10, 20, 30, 40, etc. And I put student 2 right here with a stopwatch, student 3 with a stopwatch, and so on. And I'd give the first student a pistol, and the rest of them would get stopwatches all the way down. And so, so in that box, I'd probably put like chalk marks on there. So I probably would have checked the stopwatches, tape measure, so that way I can measure, right, this is tape. Right, we have to measure that distance. We need a tape measure. And I'd probably get like chalk marks or something like that. So I checked the chalk, the tape measure, the stopwatches, and the starter pistol in the first part. And I've already started kind of outlining the procedure, which is you put marks every 10 meters and put a student at each mark. Each student has a stopwatch, except for the first one, who just has a starter's pistol. And each student starts their stopwatch when they hear the pistol sound. And each student stops their stopwatch when they see the runner pass them. And so what we're going to get is that we'll have position and time data points for each student, right? So student 1 would have x equals 0, time equals 0, right? That's this. Student 2 would have x equals 10, t equals, let's call it t1, right? Whatever the student measures, whatever the stopwatch says. Actually, I'm going to write it in blue so it matches color, right? Whatever the stopwatch says. Student 3 would have x equals 20 and t2, and so on, right? And this just we'd record all our data right like that. And that pretty much answers part B right there. Like I've said it in words, right? I've explained how I've used all the equipment. I've got my data recorded, and I've kind of got my experimental setup up there labeled, right? That's what it would look like. That's the sort of picture distance. Now, part C, the data analysis. What do we do with this data? Well, you've got a data table, and hopefully if you've kind of been used to what we've been doing in labs, if you have a data table, the best thing to do is to make a graph. That's not the only way, but that's the first thing I come up with, right? And so I'm going to draw kind of a sample graph, right? You could plot this with either time or position on the x-axis. It doesn't really matter. It kind of actually in this case, actually I'm gonna do it. Normally you're used to putting time on the x-axis, but really the position is the independent variable here, right? You pick to put them at 10 meters and you measure the time. So really it should look kind of like this, but you could do it either way. It doesn't actually matter. And so x, we have data points every 10 meters, right? All the way out to 100. And the time is whatever we measured, T1, T2, T3, and so on. So we have one data point right here. To travel the first 100 meters is going to take the first 10 meters is going to take a relatively long time. The second we know takes a little less. Again, these numbers are made up, which is why I don't have a value on that axis, but it has to be something smaller, right? This is T1, and this is T2, and then T3 is a little less of a gap again, T4 even less a gap, and at some point it stops curving and becomes roughly linear. And the reason I plotted like this is because, again, I know what kind of motion was described. A constant acceleration for the first part, and then a constant speed for the rest. And that means that this first part is curved, right? Quadratic. And then this second part, actually let me do it in a different color, is linear, right? That's what a constant velocity motion looks like, linear. And so the time at which this transition happens, right here, where it switches from being quadratic to linear, this is what's called TU. That's ugly. Right? The time that he accelerates uniformly for. So that's how you get TU, just from making the graph and figuring out where it switches from quadratic to linear. Yeah, right. It's just about visual part. Calculating the acceleration itself, what that value is a little bit trickier. But we know what equation describes this part because we know kinematics, right? We know how to write an equation for that. We have x equals x naught plus v naught t plus 1/2 a t squared. And so x naught is 0, v naught is 0, so we have x equals 1/2 a t squared. So if we go back to our graph, that's the equation we're going to use, this part right here, right, just sort of do a visual best fit line that's quadratic, kind of what I drew, and then pick a point on your best fit line, not the data points, right? This is on my best fit line. There's my x, there's my t, and we take that and plug it into this. Right, we plug it in to both x, and t. And at this point now there's only one unknown, a. So we solve. Right? So 2x over t squared is equal to a. And so we can solve for whatever the constant acceleration is. So that's approach number one. Every other approach is really just a slight variant of that. You have, if I go back to my original, you have x and t data points. You could calculate a velocity, right, delta x over delta t for each pair, right? So this would be 10 minus 0 over t1 minus 0, right? That would be, right, that would be like v average velocity for the first time interval, and so on. So you could calculate that straight down, and then you could plot velocity versus time rather than acceleration versus time. And so if you plot this, right, what you're going to get is something that looks more like, roughly again, a constant increasing velocity and then a constant velocity. And so once again, you figure out t by where the graph shape changes. That's the same. And then this is described with an equation, right? V equals v naught plus at, but v naught is 0, and so basically we just calculate the slope of that line. That's the acceleration, right? Same idea. You could do that. You could also sort of carry this out one more step and calculate the acceleration from delta v over delta t for each pair, and then plot the acceleration versus time, and then you'd have a part that's got a constant value and a part that's 0, and that would again indicate the time that you're accelerating versus not. And then the value of the constant part in the first part of your graph would be your constant acceleration. I think I would either do the velocity plot or the position plot. It's sometimes hard, like a quadratic is sometimes hard to make a good fit to, which is why it sometimes makes sense to do the velocity graph. But it's also really easy just to plot your original data. So either the position versus time or velocity versus time graphs give you roughly the best way of doing it. But either of those is really, I think, the easy way to go.